कितना दिन है? अच्छा, फ्राइडे तक का है ना? कितना दिन है? अच्छा, फ्राइडे तक का है ना? अपना ऑडियो ये ओडियस मिलेगा अपना ऑडियो ना। कितना दिन है? अच्छा, फ्राइडे तक का है ना? अपना ऑडियो ये ओडियस मिलेगा अपना ऑडियो ना। कितना दिन है? अच्छा, फ्राइडे तक का है ना? अपना ऑडियो ये ओडियस मिलेगा अपना ऑडियो ना। कितना दिन है? अच्छा, फ्राइडे तक का है ना?
Welcome, Apoorva madam.
या गुड मॉर्निंग.
Good morning, good morning.
सो मी आहे इथे म्हणजे
हो
मस्त करू आपण सुरू.
हो चालेल चालेल
हा.
चालेल.
दुसरी मॅडम आहे. गुड मॉर्निंग अपूर्वा मॅडम.
या गुड मॉर्निंग अमित.
Yeah. I have given you the host right to. You can share
ओके.
at that. We will share after 10 minutes. We do
या
not
या
share
विल
immediately.
स्टार्ट इन 10 minutes, नो
Great.
प्रॉब्लेम. ओके. Those participants who have already joined, in PSO, I am going to take one illustrative example also, which we will solve on paper and pen. So it would be great if you can have your pen, paper, or whatever in which you want to write. It will be easy for all of you to understand PSO that way. So maybe after 40 or 45 minutes, we will be solving one problem today. Okay.
Okay, madam.
Yeah, great, ma'am. सिस्टम पे कर रहे होंगे तो सिस्टम पे ही कर लेते. नो इश्यूज अपने को. आप फोन पे करेंगे पूरा दिन. मैं आपको राइट से बोलता हूँ. बिकॉज यू हैव टू ऑल्सो म्यूट ना. वॉइस इज गुड. मैं आपको पहले राइट दे देता हूँ. जिन्हें भी होता है.
अमित, मी स्क्रीन शेअर करू का?
Yes, madam. Visible, madam.
ओके, स्टार्ट करायचं मग आपण.
Yes, it's 10. We are ready to go.
या, ओके. So, good morning, everyone. I am Dr. Apoorva Shastri. I am currently working with Institute of Artificial Intelligence as Research Assistant Professor in MIT World Peace University, Pune. Today we will be covering particle swarm optimization and the illustration of particle swarm optimization. So basically illustration, I mean that we will be taking one problem and we will solve that problem using the steps of algorithm on pen and paper. It is always you can say it is always helpful for us whenever we are going to code or whenever we are going to implement any algorithm. Uh, Before implementing the algorithm, if we solve the algorithm using paper and pen, if we check the values which are coming, if we cross check the solutions which we are obtaining using the using those steps which are given in the algorithm, then it becomes easy to find out if we are going wrong somewhere or if we need to cross check certain steps again and again while coding the algorithm. So this is our practice which we follow, that we always write or solve the algorithm on pen and paper first, and then we code the algorithm. So you can use any language, you can use MATLAB, you can use Python or any any language you are comfortable with. So that is not an issue. So just a request that if you can sit with paper and pen with you, then it becomes easy for all of you to solve the problem, and you all will understand PSO at the end of this 2 hours lecture. Before going before starting PSO, I'll just give little introduction about in which field I work. So basically, I completed my PhD recently in August 2022. I am into algorithm development. So basically, I have developed multi-code intelligence algorithm. You can see the paper on the screen. So multi-code intelligence algorithm, expectation algorithm. So you can say that I am into computational algorithm development, and then its implementation, its testing and implementation on real world problems. I am from Nagpur. I have done all this diploma, degree, and MTech from Nagpur University, and I was working with a couple of colleges from Nagpur before joining in Pune. After completion of my MTech, I joined Symbiosis Institute of Technology. I worked there for 8 years. And at the time of completion of my PhD, I got better opportunity of research. So I am into research now. You can say it completely into research. So the algorithm which you can see on the screen is a multi-cohort intelligence algorithm. Tomorrow and day after tomorrow, we are going to cover one topic which is known as cohort intelligence algorithm. It is a modified and advanced version of that algorithm only. So here we have modeled a real-world scenario of intra and intergroup learning mechanism of society, where all the people try to interact and compete with one another, but their inherent goal is common. So it becomes easy to achieve the inherent goal which is common for everyone. At the time of this multi-CA algorithm is, I have published this in 2018. This algorithm, I mean, I'm really proud to say this, that this algorithm is worldwide used for research. So some examples are given here on the website, here on the PPT. So I mean, researchers from University of Kansas and University of Tongji University, they are using this algorithm for their PhD work, and they have published very elite papers. Also, you can see the publication. One is in Journal of Energy Resources Technology, and one is in Neural Computing and Application. So. It is not just restricted to algorithm development, but we are more focused on that these algorithms should be used, or should be useful for other researchers also. So as the application areas are not restricted, so these algorithms can be implemented in different application areas. I have done my diploma in electronics and telecommunication, degree in electronics and product design technology, MTech in VLSI, and then my PhD in, you can say that, artificial intelligence optimization. So here people are from various branches. I have seen that AIML is there, computer science is there, as well as couple of faculties are there from electronics and telecommunication branch also. So no need to think that the application areas are only restricted to computer science or AIML. As I am from electronics background, we have used these algorithms on a couple of applications which are related to electronics. One example I can give you is micro needle, or a needle which is used for PCB drilling. So we have manufactured. I mean, we have done the experiment on manufacturing of that needle, and then optimization of the process parameters of the needle. One of my student long back in, you can maybe 2016 or 17, she used a cohort intelligence algorithm for VLSI floor planning to reduce the area and to optimize the power. So the application areas are not at all restricted to any specific discipline or any specific branch. If you have never studied artificial intelligence, if you don't have any background of AI, or if you don't have any background of optimization, still you people can work in this field with a preliminary knowledge and some updates which you can do. During my PhD, I have published one Springer authored book, which is a socio-inspired optimization method for advanced manufacturing processes. So this book is based on the multi-cohort intelligence algorithm, which I have developed, and its applications on abrasive water jet machining, micro drilling, milling, turning, micro machining problems, as well as electro discharge machining, and certain different examples which are related to advanced manufacturing. Recently, one edited book is I have published. It is based on AI based meta heuristics for information security and digital media. It is with CRC Press, Taylor and Francis. Two more books are coming, which are edited books. They are from one is from smart grids, and one is based on enterprise data intelligence. I will share the link with all of you maybe at the end of this lecture. So if you think that you have something which can be appropriate for those titles, then you can submit your you can say title, or tentative title and author about that book to me on my email ID. Now let us start with particle swarm optimization. Before moving towards particle swarm optimization, let us just again revise what we have covered, what Dr. Kulkarni have covered in last 2 days. So basically, optimization is, in very simple terms, doing the most with the least. Now, the purpose of optimization is to achieve the best, or I mean, you can say best among what is available relative to a set of prioritized criteria or constraints. Now, whenever we talk about optimization, it is doing the most with the least. So increase the efficiency. You can say, in case of like VLSI floor planning, you can say decrease the area. Okay, so we want miniaturized versions of ICs, or the components which we are mounting on a PCB board. We want the area as minimum as possible, but at the same time, we want to optimize the power also, because if power consumption is maximized, then there is, then area minimization is of no use. This is a type of, you can say, conflicting objectives. One is increasing, so other one is decreasing, or both are increasing. So these type of scenarios are there when we talk about optimization. And optimization is a technique to the efficiency by improving the process. So like in case of manufacturing processes, we have to optimize the process parameters. In case of VLSI design, or you can say antenna designing, we have to optimize the parameters which are available for designing, so as the area can be optimized. Now, whenever we talk about optimization, any optimization algorithm, you must have heard about the terms that exploration and exploitation. When we generally compare the algorithms at the type of comparison, authors usually write about that this algorithm is weak in exploration, or this algorithm is weak in exploitation, or we have very, our algorithm is excellent. Exploration or exploitation. So, what are these terms which are available, or why these terms are continuously used in algorithm? So, before going towards direct algorithm, because previous 2 days we have seen the basics of optimization and genetic algorithm. Now, when we talk about particle swarm optimization, cohort intelligence algorithm, or you can cohort intelligence algorithm, and colony optimization, we need to think about how to find a global solution. Now, when we talk about a global solution, then exploration and exploitation are very important terms for which we tune the parameters. Now, exploration and exploitation is in general also in our day-to-day life. I'll give you example. First, let us go with the definition. So, exploration, here you can see exploration is the ability to evaluate candidate solutions that are not neighbor to the current solution. This operation serves to escape from local optimum. Okay, so we can say that when we are running a certain algorithm gets trapped into the local minimum. So what is the trapping into the local point is that the global solution is far away from the local solution, but still the particle or the candidates or the variables, they just stuck into the local point. We want that the candidate or the particle should come out of that local point and try to search for the global solution. Now, what is exploitation? It is when a search is done in the neighborhood of the current solution, it can be implemented as a local search. In simple terms, exploration is the process of searching a wide area of search space for promising solutions, whereas exploitation is the act of confining the search to a small area of the search space to refining the solutions. Now, here from this example, you can see which path should I take. Search more widely by changing the scope, search in more detail within the range what is already well understood. Now, if we take this example as I guess maximum, I mean many of the faculties are from engineering background. When students decide after, students are on the verge of deciding what to do after 12th. So at that time, they generally think that either they can go for a commerce background, or they can go for engineering, or they can go for medical, or some other branches which are available. So that is what we can call it as exploration. Search more widely by changing the scope. Am I fit for medical? Am I fit for, you can say, engineering? Am I fit for maybe CA exam? Or some other fields which are already available there. This is exploration. Now once I have decided, or once the candidate have decided that he or she wants to do engineering, then they start exploiting that the direction which they have already decided that okay, we want to go for engineering. Then they will exploit that search space. And exploitation means what are the branches available: electronics, computer science, IT, AIML, and like nowadays robotics is there. You can say mechanical is there, and so many other branches are there. They will exploit that search space. Once they have decided, okay, let us go for electronics and telecommunication, or let us go for computer science, they try to exploit it more. And exploitation and exploration go hand in hand. It is not like once exploration is done then just exploitation. No. When once you have decided that okay, you want to go for electronics and telecommunication engineering, but in that also maybe you need to explore what is there in electronics and telecommunication. Do you want electronics degree with some honors or minors, or major with computer science or something like that? So that time again you need to explore and again exploit the field which you have decided. So this is how exploration and exploitation go hand in hand. And this exploration and exploitation is very important concept when we study about the, or when we talk about any algorithm which is there in AIML, or you can say optimization. So is the concept of exploration and exploitation clear? Any question on exploration and exploitation?
Participant, if you have any doubt or you can have any question, you can put
You
in
can
chat.
ask later on also, but right now, if you want to ask anything about exploration and exploitation, or should I go ahead? Okay, I guess Amit, we should go ahead.
Yeah.
Yeah. So then
Sachin,
this,
Sachin is having one query.
yeah, please.
Sachin, Mr. Sachin, you can turn on your mic and you can ask the question.
Or you can write in chat box also. Maybe Amit can read it for me.
I think by mistake he have
No, no
there.
problem, no problem.
Okay.
These are very basic concepts. Faculties might also be knowing
Right.
those. Now, this is what we have already seen in day before yesterday's lecture, that there are local and global minimum and maximum points. So you can see this curve which is given. Now, in this curve, this is global minimum, and this is local, sorry, this is global minimum, and this is local maximum. Okay, and this is local minimum. Now local minimum or local maximum can be there in more number. Out of that we need to find global minimum and global maximum. So on this curve you can see that this is the maximum point of the curve, that's why this is the global point. And on this curve you can see this is the minimum point or minimum contour which can be noticed visually also. So this is a global minimum. Now, unimodal versus multimodal functions. This is also you have seen yesterday, but this is again a concept which we are going to use. So, unimodal functions, there is local and global optimum point, and initial guess. If we start from this, then there is this gradient, and from this gradient, the minimum point can be optimal. When we talk about multimodal function, then multimodal functions are something like this, which you can see here on the screen. So this is a local point, this is a local point, this is a local point, and this is also a local point. Out of all these local points, if we talk about the minimum, then this is the global minimum. Okay, so this is a global optimum point, or if we talk about maximum, then this is the global maximum point. Okay, these are some benchmark functions. This is a sphere function, this is a unimodal function. Here, somewhere near here, there is a global optimum. Sphere function has a global optimum point at 0. So f of x value is 0, and it is for all the x values to be 0. So sphere function which we have solved, That sphere function, we have solved for 30 variables. So x1, x2, x3, x4, these variables are x30 till x30. And we have solved, this is, you can say, simplest function. If you want to start with optimization, if you have already algorithms which you have coded or something, then start with sphere function. Sphere function has the limits of minus 5.12 to 5.12. So the area or the search space for the sphere function is, you can say, 5.12 to minus 5.12. So in this search space, you can find for the x values, that is the variables, and you can find for the solution also. This is Ackley function. This is a little bit difficult as compared to sphere function, but not very difficult. Here in Ackley function, you can see there are multiple local solutions. Okay, and this is a global solution. So, what we were talking about, getting trapped into the local minimum and then coming out of, so solution can get trapped here somewhere, and then it becomes difficult for the solution, or it becomes difficult for the particle or candidate to come out of this solution and then again jump into the global solution. So this is also very important, to what you can say, continuously perturb the exploration and exploitation while doing the optimization technique part. Now, uh, why we are going for swarm, swarm intelligence, or you can say evolutionary intelligence, when we already have contemporary techniques or exact methods which are already available. So why we are going for, you can say, these intelligent algorithms, when we can solve the problem using exact methods. So many of you have attended the 2 days lecture previous day. So can anyone give me idea that why we need intelligent algorithms when we are already having the exact methods? You can write your answer in chat box also if you don't want to turn on your mic. Any guess? That we already have exact methods. You can say branch and bound, some methods like that. So why we are using the intelligent algorithms, or why we are developing the intelligent algorithms?
Ma'am, we are getting the answers from the
Okay.
participant in the
Okay.
chat box.
Just a sec. In this Google Meet, once you share the screen, you are not able to see anything else. Huh?
Right.
Yeah. Okay. So to get the accurate and optimum solution, okay, but we use exact methods also to get the accurate and optimum solution. Anything else?
Um, one faculty, Nisha Mankhade madam, have been told about the optimization.
Yeah, optimization. These are the optimization methods or techniques. But I am asking them, when we already have exact methods that by doing this we will get the solution, then why we are using intelligent algorithms, or why we are developing intelligent algorithms to do all this? Why PSO if you already have a method? Many people are there from AI ML also, computer science also. Any
Dr.
answer?
Dr.
Easy to
Bhavna
implement.
is Dr. Bhavna is saying
Okay.
easy to implement, right?
No, no, they are not that easy to implement.
Right.
Less mathematical. Algebraic mathematics is more. So if you don't have a base of, if you are not very good at mathematics, but still with algebraic mathematics, you can use. Nisha ma'am is saying fast and less computational complex. Okay. So
Number
computation.
of variables.
Yeah, just a second, Prof. Karuna. So, Nisha Vankere raised a very good point about computational cost. So, this is one aspect which we should be talking about. Yeah, Prof. Karuna, please.
Number of variables we can, lots of
Increase.
number of variables
Yeah,
we can
yeah,
include
we can
into
increase.
this.
So number of variables are again related to computational cost only. As we increase the number of variables, computational cost might be increased, or definitely it will get increased. But we have this ease of increasing the number of variables. So I will give you a very small example, okay, from which you can, I mean, actually think about this heuristics and meta heuristics. Before going for heuristics and meta heuristics, you can just raise your hand. I have a question that how many of you have already worked in this, I mean, algorithms and nature inspired or optimization field? How many of you are already working in this field, or how many of you have some, I mean, certain papers or some research in this field? Like many of you are from AIML and computer science, so this question. Like 90 participants are there. Any of you have ever used any algorithm or implemented any algorithm till date? Okay, no issues. So I can assure you, because I have recently completed my PhD, so I have done everything from the scratch, that PSO and cohort intelligence, these are the two algorithms which you will be able to implement at the end of this FD. So those who have never implemented or used any nature inspired algorithm, so or optimization algorithm, this will be like a hand holding for all of you. So those who actually want to work in this field, they will be able to write the algorithm, decode the algorithm, code the algorithm, and we will provide you with the basic codes also. Okay. So and in the chat box, I've seen something that Suruchi did. Okay. Prof. Suruchi, can you tell me which algorithm you have ever used? Okay, let us go ahead because we want to start with the illustration part also. ABC, okay. Artificial bee colony. Nice. Okay, so here you can see uh, one example of heuristic is given here. What is this? This is a bobbin, okay, which is used for tailoring purpose. Now this is a special purpose machine, okay. This if you can see in the GIF, that every time the roll of needle, bobbin and the thread is same, that it is getting winded on the bobbin and it is doing the stitching work, okay. So heuristics are the algorithms which aim to find a good solution to a problem in reasonable amount of computational time, but they are for a special purpose problems or special purpose machines. When we talk about some intelligence, when we talk about certain things which are not special purpose, they can change with respect to time, the data can change with respect to time, then in that case heuristics are of I mean we can say heuristics become redundant, and in that case we need to go for a meta heuristic. So meta heuristics are high level strategies that combining lower level techniques for exploration and exploitation of the search space. Heuristics, I mean meta heuristics, have you seen I mean, you all must have played this tic tac toe. Okay, so that is one of the example of meta heuristics, that there are n number of possibilities. You can play like this. Some other person can play like that. So that is a meta heuristic. Now, meta heuristic refers to the algorithms which include evolutionary algorithms, swarm intelligence, genetic algorithms, differential evolution algorithm, evolutionary programming, simulated annealing, taboo search, and many other algorithms. Okay, now as we don't want to work, or not we cannot say that don't want to work, but we don't have a problem specific approach for research. Problems can be from varied fields, and we want that algorithm should be adaptable enough as well as robust enough to get acquainted at the time of description or initialization of the problem, we use meta heuristic. Second thing is computational complexity and variables, as rightly said by some faculties in the FDP. So that is also one of the things why we use meta heuristics. Now, fundamental properties of the meta heuristics. Meta heuristics are strategies that guide the search process. The goal is to efficiently explore the search space in order to find optimal solution. Meta heuristic algorithms are approximate and usually non-deterministic. Okay, so that's why we generally call them as approximation methods. And meta heuristics are not problem specific. So this is one very important thing, that they are not problem specific, and that's why generally when we already have contemporary algorithms, we try to implement, modify, or model the real world scenarios as new algorithms. Now let us talk about swarm intelligence. When we are going to study about particle swarm optimization, then this particle swarm optimization has base of swarm intelligence. Any attempt to design algorithm distributed problem solving devices inspired by the collective behavior of social insect colonies and the other animals of the societies. This is a you can say paper and pen definition of the swarm intelligence algorithm, or swarm intelligence, or the immersive collective intelligence of the group of simple agents. Now, let us simplify this more. That you can see here, there is a swarm of people who are standing on the right hand side. Okay, there is a swarm of people. Okay, what are the characteristics where we can use swarm intelligence algorithm? That it is composed of many individuals. There are many individuals. Individuals are homogeneous, so you can see that all are similar looking, all have similar characteristics, so they are from the homogeneous background. Now this homogeneous you must have studied at the time of sampling also. So in sampling, if the group has a homogeneous sample, so all students are from MTech, all students from BTech, this is a homogeneous group. Okay, local interaction based on simple rules. They can locally interact with one another in order to find the global solution. This white highlighted person is a global solution in this case. And self-organization, no centralized control. So they decide among themselves that with whom to interact, how to interact, who is the best among all, and they do the local interaction and then finally achieve the global solution. Here are some examples which are there in the nature for swarm intelligence. So this you can see flock of birds. Okay, this is colonies of bees. This is colony of ant. Not colony, but ants are going towards. Maybe you can say food or some other source where they are traveling in one straight line, and this is schools of fish. From this concept only, what you are seeing on the screen, from this only, this particle swarm optimization, which is a stochastic algorithm technique to solve computationally hard and difficult problems, came into picture. PSO, this particle swarm optimization is a robust method for optimization. Robust as in, when we will solve the PSO problem, that time I will explain this concept of robustness also. So this PSO, in short, is based on the movement and intelligence of the swarms, what we have seen here. Okay, movement and intelligence of the swarm. Now, this PSO algorithm was developed by James Kennedy. This is James Kennedy and Russell Eberhardt in 1995. Okay, a population-based search method. Population based because there are colonies, so we are talking about population. So population based positioning of particles is done in this particle swarm optimization, and every particle is treated as agent. PSO is robust evolutionary optimization technique based on the movement and intelligence of the swarm. About robustness we will talk while solving the illustrative example. Now, in this particle swarm optimization, here you can see these are the birds and they are targeting this bee. Okay. Now, this bee is their food. So, this is a global solution. Okay. and all these birds are traveling towards the bee. So these birds are nothing but particles, or you can say agents. Okay. Individuals interact with one another while learning from their own experience and gradually move towards the goal. So might be this bird is following this bird following this bird. This bird feels that this bird should follow this bird, or they can follow their own position also. So this is learning from their own experience or learning from others also. Bird flocking is one of the best examples of PSO in nature. Now, in PSO, a swarm of N particles communicate either directly or indirectly with one another using search directions. About these search directions, velocities, global based, local based, everything we will cover up in coming PPTs. The algorithm adopted the algorithm adopted uses a set of articles flying over a search space to locate the global optimum. During an interaction of PSO, each particle updates its position according to its previous experience and the experience of its neighbors. Uh, you, you might have never seen that birds are traveling in any direction. Like one bird is going there, one bird is going there. Ants never travel in like variegated directions. They try to follow the leader, and the process of deciding a leader and finding a food source is nothing but this particle swarm optimization. Now, a particle swarm optimization is composed of three vectors. The x vector that records the current position, that is the location of the particle in the search space. The p vector, that is p best, records the location of the best solution found so far by the particle. And the v vector that contains a gradient or direction for which the particle will travel in if undisturbed. Now, let us assume that this is a search space. Okay, and we have five particles: 1, 2, 3, 4, and 5. This is particle 1, this is particle 2, particle 3, particle 4, and particle 5. These are their current positions. Okay, these current positions are nothing but this p best. Okay, personal best, as this is the one iteration we are talking about. So this is their personal best location found by them so far. Now every particle is trying to move towards a global solution. Let us assume that global solution is here somewhere. Okay, so these particle will try to move with certain velocity. So this is the direction of the velocity. Okay, and then with number of iteration or number of function evaluations, all the particles try to achieve this global solution. Okay, and this global solution, okay, this global solution is nothing but the global optimum which we are trying to find out. That's why we talk about the x vector, that is their current position, x values, variable values, p vector, that is their best position obtained so far, and v vector, the velocity or the direction or the gradient in which they are traveling. Now based on these p based value, g based value, and you can say the x values and the velocity, we try particles try to find the next position. Okay, now this let us talk about PSO search scheme, then PSO algorithm, and flowchart, and then we will solve a actual example. So p best, the best solution achieved so far by the particle. G best, the best value obtained by the particle so far, by any particle in the neighborhood of that particle. So why we are talking about G best and P best, that when we work in a group, so when particles are there in a group, they try to analyze their own behavior, that is their personal best solution achieved so far, as well as they try to see where the group is heading, what is the best possible obtained by the group. That's why this G best position is also very important. So when the particles are there in the group, their personal best position as well as the global best position obtained by the group is very important. The basic concept of PSO lies in accelerating. This accelerating is nothing but velocity, which we talked about in last slide. Each particle towards its P best and the G best locations with a random weighted acceleration at each time. So this random weighted acceleration, inertial weight, these coefficients we will see at the time of calculation of the velocity. The formula is there. Each particle is treated as a point or a candidate solution in n-dimensional space, which adjusts its flying according to its own flying experience as well as the flying experience of the other particles. So this is a PSO search scheme in general. Now let us see the flow chart in detail. You can, online you will find 2-3 different types of PSO flow charts, finally leading towards these steps only. Flow chart, I have, you can say, to explain more. I have explained here the steps in detail so that you all will understand. Okay. Let us start the algorithm. So here we are. Okay. After starting, we need to initialize the random x positions, that is nothing but particle positions, and velocity vector for each particle. Okay. Then we will be evaluating the algorithm for each particle. So let us say if we have 5 particles, then we have to do this process for 5 particles. Okay. Particles are different. P1, P2, P3 are different. Variables are different. Okay, variables are x1, x2, or the number of variables you have decided. So for every particle, there will be a number of variables. Okay, and then there will be one fitness function. So like for sphere function, it is summation of xi square. Okay, so this is nothing but a fitness function. After evaluating the fitness function for the particular value, what are the x values? We need to again go back and search those x values as well. Okay. After evaluation of the fitness function, we have to check whether the fitness function is greater than the global best and whether the fitness function is greater than the local best. Now, here you can use the greater as well as the less than sign. Why? It depends on the problem, nature of the problem, that whether you are going for maximization problem or minimization problem. The current fitness which is obtained, if it is less than the global best, okay, then definitely global best will be updated in case of minimization. If the current fitness which is obtained is greater than the global best solution, then global best solution will be updated if it is the maximization problem. And similar is the case with p best value as well. After doing this, we need to check whether the stopping criteria is satisfied. Now, what are the different stopping criteria? Then, I can list out maybe 2 or 3 stopping criteria. One is if the number of evaluations, function evaluations, or the iterations are complete and still exceeding, then that could be one of the stopping criteria. If the global optimum solution is achieved, then that could be one of the stopping criteria. Or if there is no improvement in the solutions with past 2 or 3 iterations, then it means that we can say either the algorithm is saturated or the convergence is achieved. So these are the different criteria which we need to take into consideration. Now, if it is not achieved, then what we have to do? Then we have to go again for each particle. Go back to the step 2 and do all these steps which are given. While while we have calculated the fitness functions, global best and local best. After that, we need to update the velocity for next iteration. Updation of the velocity is based on the standard formula for PSO. Okay, so there is here you can see. This is the inertial weight, W. Okay. T is the iteration. So for 0th iteration, whatever the values are available for P based and G based will be the values for that iteration. Okay. For next iteration, we will be doing 0 plus 1. So iteration will be first iteration. So those will be the updated velocities, and we need to update the velocity. If we have 5 particles, we need to evaluate this formula 5 times. For every particle, we need to update the velocity, and for every particle, we need to update the position, and for every particle, we need to find out the fitness value. This inertial weight W, you can take it in between 0 to 1 right now. Then you can decide these values based on the preliminary trials and the nature of the problem you are solving. These VT values, this T is nothing but 0. So in previous iteration or in the first initialization part, whatever the velocity values we have initialized, those will be taken here. And this C1 and C2 are nothing but acceleration coefficients which we talked in the previous slide. This accelerating weighted acceleration, so these are those coefficient. These coefficient values can be taken in between 0 to 1, as well as you can take this value 1 to similar values. Those all this is based on the preliminary trials. Then updation of the position, whatever you have obtained in the first iteration, okay, those values plus velocity for the next iteration will give you the updated position for the next iteration. Then this will be done for the next particle, and this is how particle swarm optimization works. How exactly this is achieved, how this algorithm or how this flowchart actually works, for this we will be solving an illustrative example. Any confusion or any doubt in this flowchart? Any question? Amit, please let me know if there is any
As
question.
of now, there are no questions.
Okay.
Hello?
Yes?
No question, ma'am.
Okay, okay.
Can you can we resemble this value of T1 with the instances?
Uh, just a second. Your volume, I mean, I'm not able to hear you. Just a second.
Can you please louder?
Uh,
Yeah.
can we resemble the value of P1 with the instances?
With the instances means, can you reframe the question?
Means records.
Records means which records you are talking about? The data set which is available with you?
Yes.
Okay, so see the x variable values which we have taken. Okay, these variable values we are taking with from some random search space with some random instantiations. Okay, so if you have a data set on which you want to use the PSO, then that data set first needs to be checked whether that data set is, I mean, limited data set is there, or how many number of variables are there in the data set. And depending on that, we will see that how this PSO can be related to the instances which are available with you. But definitely with the available data set, PSO will be used, I mean, can be used. Is that okay?
Ma'am,
Yeah.
can I say that number of databases, size of databases, and the number of variables can first. These are the things that I have to check first before
Okay.
applying in PSO.
Yeah, see, not only for PSO, this is the case for every algorithm. That if you have a data set available with you, and if you want to work on that data set, then definitely optimization algorithms are the one which can be used on that data set. Okay, but then we just need to check that how many number of variables are there, and what are the parameters which we need to tune for that data set. But definitely PSO can be applied on that data set. So once we are done with this illustration part, no, you will come to know that how, I mean, you can relate it with your data set. That's why we are doing the paper and pen illustration thing today.
Tune means not getting, madam.
Huh?
Tune.
Yeah, so we have right now I'm talking about the inertial weight W, C1 and C2 acceleration coefficients. So right now for solving one illustrative example, we will take some value of that C1, C2 and W. Okay, but it is not the case for every problem or every iteration also. We need to change the values, or we need to tune the parameters in such a way that we will obtain the global solution. So this is nothing but tuning. So we need to make algorithm intelligent and smarter in such a way that the parameter tuning should also be done in the algorithm itself. Okay.
fine.
Yeah. So once we will start with the illustration part, these doubts will be cleared. I guess, I mean, that will be more detailed version of what we are talking about, flowchart and all. Okay. Yeah. Okay. So now algorithm implementation. The basic concept of PSO lies in accelerating each particle towards the best position found by it so far, that is P best, and the global best position obtained so far by any particle. So this is what we have seen. This is the formula for obtaining the next position. So xi plus vi, that is an x vector. Once the particle computes the new position, that is xi, it then evaluates its new location. If x fitness is better than p fitness, the p best will be updated. And I mean, this is what we have seen in the algorithm, that if the fitness value is better than the global best value, global best will be updated. At the same time, local best will also be updated. Now, this is the particle, its current position, okay? This is the best position obtained by the particle so far, and this is the global best position obtained by the group so far. Now, how we move towards the next best position is what we are trying to achieve using the PSO. So, this is the formula which we have seen in the algorithm or in the flowchart. Now, if a geometrical illustration of the algorithm you want to see, then particle will travel in the direction of the velocity, as well as particle will travel towards its best position obtained by the particle so far, that is local best position p best, and particle will travel towards the global best position obtained by the group also. So this is the path by which particle will try to find out the new position. So this is the updated global best position in the next iteration, and this can be achieved using this formula. Okay, so this is the acceleration, this is the inertial weight, these are acceleration coefficients, and this is the p best value, and this is the g best value. Now taking into consideration all these things, we can find out the new global best value for the particle, and this we have to do for the every particle. Now let us start with the numerical example. I want all of
Ma'am, how to choose the best path by the particle?
Yeah, so this best path is chosen on the basis of these three things: its velocity direction, its personal best location, and its group's best location. So all these, these three things are taken into consideration while achieving or while taking the decision about the best possible path or best path for the global best solution. So particle cannot move always in the direction of the velocity. Particle can't move always in the direction of its personal best solution, and particle can't always go into the direction of the global best solution, because in the first or second, this early iterations, you cannot decide whether this is the global best position or not. That's why this x vector, p vector, and the velocity vector are very important parameters or initialization parameters for this particle form optimization. So particle will if you take example that we need to find out some hidden treasure, okay, and 3 4 persons are together, are working in a group to find that treasure, okay. So if you look at the top view, then you can see that I am moving into one direction, you will move into another direction, Mr. Amit will move into one direction, and one more professor will be going into some other direction. At the end of day one, we all will be at the different locations, okay, and those will be our personal best locations, because we have just covered one day. Till date we have just covered one day, and treasure is still, we need to cover a lot of distance to find that treasure. But it can happen that you are very much near to the treasure, and me and other three persons are way behind you. So what we will be doing, we will be following you as our global best, okay? But at the same time, as you are far away from us, we cannot travel directly where you are. So we need to travel in our own direction. We need to travel with the velocity what we are following, and at the same time we need to take the path which you have taken. So maybe at the end of day 2 we will cover more distance, but in the right direction where you are already, but we will not be able to reach the position where you are at the end of day 2, or or one of us can reach to your position also. So this is how we need to decide that what is the best path for every particle or every candidate, and then in that direction we can proceed, but that direction is based on these three things. So these three vectors or these three parameters are very important when we are tuning or when we are doing the solving the PSO. Are you satisfied with the answer?
Yeah, madam. But the whenever we are calculating the path,
Huh.
it takes us some times for calculating the best available paths to the destinations of this particular particle.
Huh.
So in that situations, the algorithm first of all calculate the best path.
Huh.
Then and then only it can decide, na.
No,
Yeah, at the run time it will be decide the best path.
no. The thing is, what you are talking is correct, but then this is not the case for single particle. As we are
Yeah.
right now for illustration, we are taking only 5 particles. Okay. Now
Okay. Okay.
consider the case of 100 particles.
Yeah. So in that situation, the path
Yeah.
should be calculated prior to the if you travel start this traveling.
Yeah, so that is what I am saying. At the initialization, we will just initialize the current positions of the particles. For next iteration, we will calculate the traveling path and update the positions as well. So
Yeah.
for
Yeah.
next iteration, definitely the best path is calculated, but we cannot decide the best path in advance, like so advanced, because
Yeah.
100 particles. So the
Yeah.
one scenario can be better for one particle, but not good fit for
For the
other.
multiple n number of,
Yeah,
yeah.
yeah. So this is
Okay.
the point. Yeah. Okay. So let us start with the illustrative example. We have taken the maximization function here. Okay. So f of x is equals to 1 plus 2x minus x square. Now, those who want to solve this, we will take another 40-45 minutes to solve. So you can write it on pen and paper, and we will try to solve it with iteration 1, iteration 2, iteration 3. For simplicity, here we have taken 4 iterations only. But definitely for achieving the global solution, we need more number of iterations. Okay. So our maximization problem is f of x is equals to 1 plus 2x minus x square. So every time whenever we talk about fitness, we will be evaluating this equation, 1 plus 2x minus x square. Now let us talk about the control parameters. Inertial weight, I have taken 0.70. You can take any other value also, but right now in this FDP at the time of solving, all of you, this is just a request that all of you should take this value, so that if something goes wrong, it can be checked or cross checked. Okay. So then these inner acceleration coefficients have been taken as 0.20 and 0.60, and I have considered 5 swarm particles. So P1, P2, P3, P4, P5, and for simplicity, number of iterations have been iterations taken are 4. Okay. Now before writing this, everyone please write this formula, as this is very important for all the calculations. Vt plus 1 and this. Just note down this formula, and then let's go to next slide. Okay. So we have defined W, we have defined C1, C2, we have defined number of particles, and we have defined the number of iterations. I want now this illustration part should be thoda sa, response from your side also, whether you have you are getting it, whether you have solved this step, whether you are getting next solution. So it becomes easy for me to explain this illustrative example. Okay. Then, if you can see in this formula, we need random numbers. For this step and this step, we need random numbers for the evaluation of these steps. Okay. So, as there are 5 particles, I have decided that I will be taking these random numbers which are chosen from within 0 to 1. Okay. These random numbers can also be chosen as whatever you want in between 0 to 1. You can randomly definitely generate those numbers also. Here again, just to solve these problems, I have considered these random numbers. There is no significant thing that you need to take these numbers only or you have to choose these numbers only. No, I have just taken these numbers for evaluation or illustration of this problem. In every iteration, you can change the random numbers. Okay. Again, as we are solving PSO for the first time, we are not going to change the random numbers in all the 4 iterations. Okay. So all the disclaimers are clear that there is no science behind this. Right now, for simplicity and for pen and paper problem, I have taken random numbers as these, and these random numbers are kept constant for all the iterations. You can change or you should change the random numbers in every iteration so as to achieve the more robust and bias-free solution. Okay. Done till this point, everyone? Noted everything till this point? Because you will need these values for solving the for evaluating the fitness function and velocities and other things.
Yes, it's done.
Okay. Thank you. Okay, now initialization of particles. We initialize the fitness of all the particles as zeros. So all the particles initialized as zeros, and now current position of all the 5 particles are calculated. Okay, now for calculating the current position, you can see here, this is CP, that is current position, and 0 means 0th iteration. Okay, means this is the 0th iteration. Okay, this formula 10 into random number 1 minus 0.5 is again the formula taken so as the particles current positions can be selected greater than 1, as well as positive and negative positions can also be selected. If you don't want to do the current position selection by this formula, you can randomly select the current positions also. Okay, so to have some logic why we have selected this position, so I have multiplied it by 10 to initialize at least some particles to be greater than 1. Okay, and subtracted 0.5 to generate both positive as well as negative position, so that complete search space can be covered, and you can see that how particles travel towards their personal best, towards global best, and like that. Okay, so this is the formula which we have used for obtaining the current position. So 10 into random number 1 minus 0.5. These are the random numbers which we have taken in the previous slide. Okay, selected random numbers from 0 to 1, within 0 to 1, and we have subtracted 0.5 from every random number, from each random number, and multiplied it with 10. So these are the current position of the particles. So this is particle 1, this is particle 2, this is particle 3, 4, and particle 5. Okay. Current position of all the particles at the initialization clear?
Yes, ma'am.
Yeah, okay. Now, let us calculate or initialize the velocity. For velocity, again, I have used one formula, R2 minus 0.5. Okay. So random numbers we already have. I have just subtracted zero point 0.5. So we will get the initial velocities at the time of 0th iteration. Again, same thing, you can directly take these values also or any values, something like this, for the initialization of the velocity. I have taken R2 minus 0.5 just to explain this so that all of you will have the same values for solving the illustrative example.
Ma'am, can we have different values for the velocity and the
Yeah,
previous?
yeah, yeah. Velocity as well as current positions. So, Amit, if we take example of sphere function, okay,
Right.
as I have said in the earlier side, it has a interval of minus 5.12, I mean, search space of minus 5.12 to 5.12. So, initial positions, okay, positions means x values, okay, not fitness function, okay, variable values can be anything between this, okay, at the as well as velocities can also be anything between this, okay.
Okay.
Yeah,
Just I'm asking a question. We have taken the current position minus whatever the random values
yeah, yeah.
minus zero point 0.5,
Huh.
and the same for velocity we have taken random
No,
values.
no. So that is what I am saying, that there is no any science behind these formulas. You can simply see that I have multiplied it by 10 to initialize at least some particles greater than 1.
Right.
Okay, because we are going towards maximization problem. Now if all the particles are having values towards 0, then definitely maximization देखने मिलेगा ही नहीं with this just 4 iterations,
Right.
right? So now we know something biased we is there in our mind that ऐसा होना चाहिए. But if I am considering sphere function, then I know that global value and local values are 0. X values should also be 0. तो
Right.
इन दैट केस अगर ये इनिशियलाइजेशन में सब कुछ जीरो से रिलेटेड भी रहा तो भी अर्ली कन्वर्जेंस में आई विल गेट द आंसर.
Okay.
Okay, so here you can subtract zero point 0.3, zero point 0.2, you can multiply with 5, anything can be done. Amit,
And that
there
will
is,
be
yeah.
different for the current position and may be different for the velocity too.
See, this is what we have to do only for the first time.
Okay.
After that, we are not going to do this because after that, there is predefined formulas by PSO which we have to use. But
Right.
from where to start?
For
Initialization.
for the
For that, we are
initialization, we
doing.
have to take
Yeah.
pump
So
circuit.
this is just for initialization. Now, when you will see a couple of other examples by other researchers, there they have taken C1 and C2 as 2 also.
Oh.
They have taken C1 equal to C2 as 1 also. So this is what I am saying, that it is based on the nature of the problem as well, that which we are going to solve. And while doing the iterations, we'll come to know that no, this is more best for, or this is the best value of C1 and C2. If I keep these values, then I'm getting the answer.
Right.
Then you can. This is what I was talking about tuning.
Right.
Okay.
Right, ma'am.
Yeah. Okay, Amin. So everyone noted the velocity values also. So you should have with you current position values and velocity values. ये दो vectors you should have right now available with you on the paper to go for the further calculations. Done till this point, everyone?
Yes.
Okay, thank you. Okay, now we will start with iteration 1, and here where the best path, global best, local best, and everything comes into picture. Okay, now don't write anything first, just concentrate on what we are doing, and then try to evaluate these steps on your own and just cross check the answer with PPT. Okay, in iteration 1, okay, we have current positions of each particle. This is what we have initiated. These are the positions which are already written with you as current positions. For iteration 1, the current positions in iteration 0 will be the current positions in iteration 1 also, because right now we have just started with the algorithm. So whatever the initial positions are available for the particles, those will be the current positions for the iteration 1 as well. Okay, and same is the case with current velocity also. that whatever we have taken at the time of initialization, those will be the values of the velocity. Okay, from these current positions and current velocities, first we will calculate. Now for fitness, take this formula: maximize 1 plus 2x minus x square. In this 1 plus 2x minus x square, put these values: minus 0.3425, 3.99, and these values, and find out the answer for fitness of P1, P2, P3, P4, P5 for iteration 1. Those who are very new, I will tell you how to write or how to understand. Particle 1, particle 2, particle 3, and iteration number 1 is common. So this is fitness value for particle 1 for iteration 1, fitness value for particle 2 for iteration 1, like this. Okay, so calculate the fitness values and just cross check whether the fitness values are right or not. Done with current fitness, CF of 1. Done with the current fitness. And please write the notations like this only: CP0, CP1, CF1, V1. Don't write anything like for velocity. Don't write any other variable. Write V only. For current fitness, write CF only. So it will be easy to understand it in other iterations. Once you are done, please let me know. Then we will find out local best and global best positions. Yes, done with this calculation. It is just a simple formula: 1 plus 2x minus x square, and you have to put these values as x values for each particle. Or you can just note these values, because every time you just have to put the values in the formula and you'll get these answers. Should I go ahead?
I think we should move ahead, ma'am.
Okay, okay. Okay. Now, can any one of you tell me that whatever you can see here as the current fitness, what could be the global best solution? Or what is the global best solution in iteration 1? ये जो values यहाँ पे है, from these values, what is the global best solution? What are we doing? Maximization or minimization? What are we doing? Maximization.
Maximization.
Then which is the maximum value?
1.075.
Yes. So 1.0755 is the maximum value. So you can call it as global best value. Okay. And for local best value, let us see now. Local best and global best values. Local best positions of each particle up to first iteration is just its current position, because we are done with only one iteration. So whatever are the values of the current position for each particle are its current best positions also. So local best position, LBP is position, LBF is fitness, GBP is position. Position means X value, and fitness means you can say objective function value. Okay. So local best position LBP1 is equal to current position of iteration 1, and these are the current positions. Okay. And local best fitness for each particle is nothing but fitness values obtained using these X values. So these are nothing but these values, and these are the current fitness, which are nothing but local best fitness. Clear till these two? Local best position and local best fitness?
Yes.
Okay. Now global best fitness of iteration 1 is maximum of local best fitness of iteration 1. So whichever value is maximum from this local best fitness 1, I just have one I just want to make one thing clear. This one is iteration number, not a particle number. Okay. Some of you can get confused in this. Don't get confused. Here we have taken only one variable. That's why there is just X. When you will take number of variables, number of particles will be different, number of variables for every particle will be different. So in this case, as we have taken only one X value, if we have x1 plus x2 as objective function, then there will be two particle values, two X values for each particle. Okay, these are iteration numbers, not particle numbers. Okay, don't get confused in that. So maximum of local best fitness for iteration 1 is global best fitness. So maximum, you all have, I mean, some of you have rightly pointed in the first PPT itself that as we are doing maximization, this is the local best fitness, and then global best fitness, and the global best position will be what? The position related to this global best fitness. So as this is the fifth particle which is having the global best fitness, the position related to this global best fitness is 0.0385. So this is a variable value, X value for particle 5, and this is a fitness value, that is objective function value for particle 5. So global best position corresponding to current position of the fifth particle is this, and global best fitness is this. Clear? Clear?
Yes.
Okay, now we have particle की best position. Particle के group ने find out की हुई global best position. Now we need to find out velocity. And then depending on these three factors, we will be able to decide that particles will move towards which direction. Just look at this slide, what we have seen. Right now we have obtained P best for the particle, G best for the group. Now we need to obtain the velocity. So this formula will be used. Once we are done with the velocity, then we will be using that x of t plus 1 is equal to xi plus vt plus 1. उससे हमें particle की next updated position मिलेगी. So right now we have this current position, we have velocity find out करके we will be moving towards the next position of the particle. If I am not taking this in full screen, still is it visible?
Yes.
Yes.
Because once I am doing full screen, I am not able to see anything, palette or anything. Okay. So यहाँ तक we are done. Now velocity for iteration 2. Okay, now we are starting with iteration 2. So everywhere in the bracket, there will be 2. Okay, so again, it is not a particle, it is the iteration number. So formula is Vi plus 1. So I is the previous iteration jo tha. So 1 plus 1, so V of 2. Inertial weight we have taken as 0.7, right? Inertial weight is 0.7. C1 is 0.2 and C2 is 0.6, and these are R1 R2 values जो हमने पहले लिए थे. Okay, so let us solve it for first particle. This step we have to repeat 5 times. Okay, so let us start for first particle. एक particle का जैसे समझ जाएगा, we will move towards second, third, fourth, fifth particle. Okay, for first particle, R1 value is this, R2 value is this. If you don't remember from where we have taken this, so you can just go to your first initialization thing, and these are the R1, R2 values. These are for particle 1, these are for particle 2, these are for particle 3, 4 and 5. Clear? And these are the initial values which we have taken. Now, for first particle, the current position of the particle CP1, local best position of the particle and global best position of the particle are also needed. If you can see here, then this is the local best position minus 0.3425. Okay, this is the local best position. Global best position is this. So global best position se related particle value is 0.0385. So we have written here 0.0385, and whatever or whichever is the current position is same as local best position in iteration 1. That's why these two values are repeated. Now let us calculate velocity for iteration 2 for first particle. So put all these values 0.7, velocity 1 is this 0.0319, this is for particle 1. Okay, then plus 0.2 C1 acceleration coefficient into R1 is this 0.4657. Then LBP1 minus CP1. So LBP1 minus CP1 plus 0.6 GBP1. This is GBP1 minus CP1. This minus 0.3425. And then just check whether you are getting this answer or not. And if you have any question in this, you can ask me. Just let me know once you are done with first particle. because we have to do this for all the 5 particles, but at least if you are able to put the values for first particle correctly, then you can cross check the values for particle 2, particle 3, particle 4 and 5 for velocity iteration. For velocity for iteration 2.
Ma'am, I have one question.
Yeah.
Velocity for next iteration, the formula which we have used, is it to be used for all the problems or it will be different for different problems?
No, this is the standard formula for PSO, for velocity calculation.
Okay, means it is fixed for all the problems we solve with this.
It is devised by Kennedy and Eberhardt. We can't change the formula. See, now there are different versions of PSO also. This is very basic PSO, which is, which was developed in 1995. So we are starting with that PSO. Now there is CLPSO, there are hybridized PSO versions. Some other algorithm with PSO. So there are different versions of PSO also. At that time, whatever that researcher have done, we can adopt that work also. But for standard PSO, this is the formula for velocity calculation, and one more formula is there for obtaining the next position. So these two are the standard formulas.
Means this can also be a point of research to research the velocity formula.
Yeah, if you want to find out some better version of particle form optimization, then you can take this into consideration as point of research. Definitely.
Right. Thank you.
So if you are able to find out some new formula, please let me know. Okay, so can anyone please update me? Are you able to find out the velocity for iteration 2 for particle 1?
Ma'am, Dr. Bhavna is having a question.
Can she ask on the mic?
How to decide C1 and C2?
Yeah, so this is what I have said, that C1 and C2 will be decided on the preliminary trials. Here we have taken C1 as 0.2 and 0.6 as C2. You can take any value between 0 to 1, as well as you can take any value as 1 or 2 also. So that depends on the problem which you are going to solve. And for that, you can refer the couple of other papers also. So these are the initial values, like tomorrow when we are going to solve CI also, there we have one reduction factor. That reduction factor can be selected in between 0 to 1, any value in between 0 to 1. So for a couple of problems, we have taken it as 0.9. For a couple of problems, we have taken it as 0.35, 0.25, something like that also. So it is like that. And one thing I would like to mention here, as thank you for this question. So for this C1 and C2, Mr. Second, I have mentioned it somewhere. So larger the C1, if C1 is larger than C2, then greater global search ability can be achieved, because you can see that the C1 is associated with this LBP. Okay, so if the C1 is greater, then greater the global search, and if the C2 is greater than C1, then greater is the local search. So you have to consider these things also when you are going to solve the problem, that where you want to focus more at the time. If you want to change, or if you want to explore more, or if you want to exploit more, depending on that, you can select the random numbers also, different random numbers for every iteration also. Okay, so these acceleration coefficients will definitely play very important role for global search and local search. Okay, any other question?
No question.
I have one question.
Yeah.
at initial iteration, can we focus on C1, that is local, and on the lateral iteration, can we focus on C2, that is on local?
So the thing is, this inertial weight C1 and C2 are generally kept constant, and they are not. I mean, we generally don't change them in between the algorithm. Okay, but if you want to change the values, then you can decide depending on the fitness function which you have obtained. If you, I mean, if you have decided, let us run the algorithm 500 times. Okay, I mean 500 iterations, and in between, at the time of 150th iteration or 200th iteration, you can see that results are not changing at all. So then you can decide that, okay, now it is stuck somewhere in the local solution. At that time, you can take a decision that you can perturb the values of C1 and C2 or inertial weight. But unless and until there is no need to change, if you can obtain the solution with the constant values, then this tuning is not needed in between the, I mean, in between the iterations.
Okay.
Yeah,
Thank
so
you.
these decisions are to be taken at the time of solving the problem, and that's why you should note, or you should save each and every solution at the time of, I mean, when algorithm is running, you should have the values of X values and all the fitness values starting from the iteration 1 till the last iteration. So depending on that calculations also, you can decide about the changing of these values.
Ma'am, one more question.
Yeah,
If I
please.
change that C1, C2 value in between,
Yeah.
so shall I start it from the
No, 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 no. If you change it in between and if you again start it from, I mean, if you restart the algorithm, then there is no point in changing the values. Then it means that you keep the values same till 500 iteration, and then you again change the values and start the algorithm. But if you want to change the values in between, then the solutions obtained using the new values and previous values should be taken into consideration while doing the algorithm.
Okay.
Otherwise, it is like you are initializing. I mean, you have started with 0 mile and again going back to 0 mile. It is like that.
Okay.
Okay. Yeah. Okay. So I guess now till this point, all of you must have obtained velocity values for all the particles. Any doubt in this? 0.1439 minus 1.7008. Any doubt in this? Should we go ahead? Or you can note these values if, I mean, if you are lagging somewhere in the calculation, you can just note these values. We still have half an hour. If you want to solve for every particle, I can wait. No, no, not an issue.
I suppose you can proceed, ma'am.
Yeah, thank you, thank you. Okay, so now these are current position. Now again, let us get back to local best and global best solutions. Okay, no, this is what we are done with. Now current position, sorry. So okay, we have for iteration 2 current positions, okay, and local best fitness values. Now these current positions, can anyone tell me from where we have obtained these current positions? CP of 2. These CP of 2, where are these values which, I mean, where are these values where you have seen these values earlier? These are CP1 values. These are velocity values. These are velocity values. for iteration 2, current position values, from where we have obtained these values. Okay, just think for a while that how to calculate CP2. Okay. How to calculate current position for iteration number 2. We have calculated the current position for iteration number 1. Now how to calculate current position for iteration number 2? We have to take maximum from previous iteration and the current iteration. So depending on that logic, try to just find out that what could be the value for iteration 2, current position of iteration 2. Or just try to calculate, or try to calculate and tell me that what is the value of CP2 for first particle. We have one formula xi plus vi plus 1 to obtain the next position. We have written one formula x of I plus 1 is equal to current position of x of I plus velocity of next iteration. Do you remember that formula? Yeah. No. Dr. Bhavna, not 10 into CP1. This was for initialization. To find out the next position, wait, I'll share the screen. Okay. This formula, xi plus vi, or we have written it earlier also. I'll just show you. Yeah, here only. Here we have written xt plus 1 is equals to xt plus vt plus 1. This x is nothing but cp, what we are writing current position cp. So cp of 2 आपको निकालना है, that is next iteration. So here will be cp1 plus velocity 2. Yeah, velocity 2, t plus 1. So if you are doing this for iteration 2, then velocity will be from iteration 2 and current position will be from iteration 1. So velocity of the next iteration and current position of the previous iteration will give you next position. Okay?
Yes.
Yeah. So we have written here just. So this is the formula. Cp is nothing but x. Okay. So what we have done here is you can see these are CP1 values, current position 1 values. These you have written it everywhere, current position values. Okay, you can see here these are current position values. Okay, and these are your velocity values. These are your velocity values. That current position plus this velocity will give you next position. So this plus this plus this plus this plus this will give you CP2. Okay. Once you have the position values for iteration 2, again calculate the fitness function 1 plus 2x minus x square. Any doubt in this CP2? Any
No.
doubt? Okay. So once you have CP2 values, that is current position 1 plus velocity 2. Okay, next velocity plus current position. So if the particle is here, okay, if the particle is here and a particle wants to find the next position, then it will check for the velocity. At the time of finding the velocity, we have considered local best P base, global best D base, acceleration coefficients, inertial weight. That's why just adding the velocity into its current position, you can find the new position. Okay, because this is not the final I mean, this is just a final formula, but logic behind the velocity we have already seen. The acceleration coefficients are there, inertial weight is there, and then this, what you can say, velocity is also there. Okay, done with CP2, done with iteration number 2. If you are done with calculation of current positions for iteration number 2, then please calculate the current fitness for next iteration. So simply put these values as substitute to X and calculate the current fitness, and let me know that what is the local best and global best for this current fitness for iteration number 2.
Apurva madam, we have one
Yes.
question
Yeah.
from
Yes.
from Mr. Datta Shingate.
Yes.
She is asking about no, he is asking about how to decide the optimum number of iterations to be carried out.
So optimum number of iterations are also decided on the preliminary trials. Okay, depending on the values, what you are taking for inertial weight and acceleration coefficients, Depending on those values, whether to increase the number of iterations or to decrease the number of iterations is decided. You can start with 500 iterations, or you can start with 300 iterations, and you can just check the results, but you should not check the final result always. You should have a matrix where the results for all the iterations is there. From that, you can see whether the algorithm is saturated on those iterations, or it is still getting the better and better solutions, but you have just stopped it on 300 or 400 iteration. So depending on that, you can decide the number of iterations. And for that, I said that you should save all the results for fitness function and current positions, means variable values and objective function.
Okay, ma'am. Thanks.
Yeah. Okay. Let me know if you are done with current fitness for next generation. Okay. So these are the current fitness values for next iteration. That's iteration number 2. From these values, it can be clearly seen that which is the maximum value, okay, for global fitness. Let us first find out the local best fitness, and then let us move on to global best fitness. Now, as we have 2 iterations, we are done with 2 iterations. Now we have to consider the past experiences of the particles, that is previous iteration, and the current iteration. That's why now the local best fitness value for iteration number 2 will be maximum of current iteration and previous iteration. So local best values of the previous iteration are these, and the current best values of the previous iteration are these. Out of these values, these 2 are for particle 1, these 2 are for particle 2. We will select the maximum values as we are doing the maximization problem. Okay, so now 0.5634 is maximum for particle 1, 0.4250 is maximum for particle 2, 0.2860 is maximum for particle 3, 1.2812 is maximum for particle 4, but for particle 5, 1.0755 is maximum, so it is taken from this matrix. So local best fitness for iteration number 2 is this. Clear with this? Everyone? Clear with local best fitness for iteration number 2?
Yes, ma'am.
Yes.
Now, we have for iteration 2, these are CP2 values and these are local best fitness values. Why this 4th value is changed? Can anyone tell me? No, not changed, sorry. Why this 4th value is highlighted? Because this is maximum of all. This is maximum of all, and that's why this is global best fitness. From local best fitness, whichever is the maximum value, that will be the global best fitness value for iteration number 2. So this is the global best fitness value for iteration number 2, and this is the corresponding global best position. Okay? Is that clear?
Yes, ma'am.
Right, ma'am.
Okay. So the global best position in iteration 2 is this for 4th particle in CP2. Okay. Now, local best positions of each particle in iteration 2 are given as this, which we have already written. Okay. Sorry. We know these are the values for iteration 1 and these are the values for iteration 2. If you see that the local best position for iteration 2 are these values, okay? Local best fitness values. But from this local best fitness value, uh, this position values 0 point this we have highlighted this value, okay, but at the same time we have changed this minus 0.1919. Why? Because as we have the previous best positions and the current best positions, if you look at the previous best position in iteration 1, then this position is better than this position. So as we are moving towards maximization problem, the particle is not doing very well with the current position, whereas its previous position is much better. That's why for particle 5, the current position is updated as the 0.0385 best position obtained so far by that particle. Okay, so current position is best for first four particles. These are the best positions obtained in the iteration 2, but not for fifth. That is why what is the reason that last one is the better. If you see this is the current position, then this value of current position is better than what you have obtained in the next position. Okay, so past experience or the present, whichever is the best value obtained so far, that value you have to consider. In global best, whatever you have as from the local best and the previous best, you have to select. For current position, you have to select whatever is the best position obtained so far by the particle. Clear? Is everything clear till this point? Is everything clear till this point?
Yes, ma'am.
Okay. Now, this is summary of iteration number 1 and 2. What values we have obtained, I have just written here. Okay. I will share the PPTs after this FDP. Okay. So, I mean, today's lecture. So, don't worry, you will get this. And this is the summary of iteration 3 and 4. I mean, the same way you have to solve for iteration 3 and iteration 4, and you can cross check the answers from here. Okay, so you can just check what you have solved. Now you again have to calculate the fitness function, you have to calculate the velocities, you have to calculate the current positions, and by doing all this you will get this global best position for third iteration, global best position for fourth iteration. Now here you can see global best position for first iteration was 0.0385 and global best position for iteration 4 is 1.05. So we have achieved this much maximization with just 4 iterations. So if we go on doing, if we continuously do this for certain number of iterations, we will achieve the optimum solution. Okay, now I mean, you can take a screenshot of this till the time we will share the PPT with you. And let us just observe the graph. If we plot the graph for this, how the graph will look, okay? So maybe I'll plot it here. Something like this, okay? Wait. Discard. So if I want to plot the curve, is my screen visible, whiteboard?
Yes, ma'am.
Okay. God, बिल्कुल सीधा नहीं निकल रहा. Okay, so these are f of x, these are f of x values, okay, and these are x values. So let us write 1, 2, 3, okay, and here again 1, 2, 3 minus, okay, minus 1, minus 2, minus 3. So if we plot the values which we have obtained for global position 1, 2, so in global position 1, it was somewhere 1, 2, 3. Okay, so the first position obtained was somewhere around 0.03, then some other position, then some other position. So if we plot the graph crossing over all these points, then the graph will be something like this. Okay, so this is nothing but a final solution plot for what we are doing. We have to plot all the points, definitely means we have to plot the x1, I mean x values also. So f of x is 1.997. Okay, so 1.997 will come somewhere here for the x value of 1.05. So x value 1.05 is here, so plot will be like this. So this is maximization. If we are doing minimization, then plot must have come something like this. Okay, so this plotting can also be one of the tool for analyzing that what we are doing is whether this is correct or we are going into some wrong direction. So if you just want to take a screenshot of this, you can take so that you can analyze the calculation. This is a global best position, not fitness. This is a global best fitness. Fitness is objective function and position is the variable value for that function. This solved example you will be able to find out in NPTEL video also by Professor Biswajit Mahanti. He is from IIT Kharagpur. So this solved example is taken from his NPTEL lecture. So if you want to go through the video for this solved problem, you can go through the lecture series on decision modeling. So there is a lecture series on decision modeling by Professor Biswajit Mahanti, and from that lecture series there is a lecture number 38 or 39 on this PSO problem solving. So you can go through that also if you want to just check about what is what are the different scenarios, how we have obtained this, something like that. Okay. So here we are done with particle swarm optimization, basic concepts. What is the swarm intelligence? Why it is? I mean, how it is implemented, and what are the real world applications and the implementation part, that is illustration. I will share a small PSO code also with you where you can just tune the parameters. You can put the code in MATLAB and you can run the code and check the answers. So I'll just stop sharing the screen. And if you have any question or if you want to know anything more about what we have studied today, then you can ask. Platform is open.
Participant, the session is open for the questions.
Or if you want to try whatever we have done, you can solve everything because tomorrow sometime I'll take the lecture one half Dr. Kulkarni will take about the background of CI, what is CI, and then from the illustration part, I will take over. So maybe tomorrow or day after tomorrow, again, I am going to take the lecture. So that time also, if you have any queries, you can ask. It is not like that we have started with CI, so no queries will be entertained about previous topics. And if you have anything right now, you can ask. Just a small suggestion that if you really want to work in PSO or any other algorithms, whatever we have studied, try to again solve it by taking some other variables, some other numbers, and just try to analyze what values you are getting. And then you can write the code, and it will be hardly a half an hour job for all the professors like you from computer science and other backgrounds. So maybe you can try PSO on your own and let me know if you have any queries.
Purva madam, there is
Yes.
one question from the Suruchi ma'am.
Is it similar to greedy algorithm approach? I actually I'm not that aware about this greedy algorithm. Maybe I'll just go through the algorithm and I will get back to you in the next lecture. Because I myself have never used the greedy algorithm, but I just need to check whether the greedy algorithm is using a gradient distance method or conjugate gradient or what. So maybe you can just give me some time and I'll get back to you. Okay, Amit. So can we stop?
Uh, i- are there any questions from the participant?
Or you can just note them down. If later on also they have questions, then you can ask me.
Okay, okay ma'am. So
Okay.
thank you for your presentation, ma'am. As
Thank
there
you.
are no questions from the participant, we are very much thank you for your presentation. It was very nice presentation, and I hope the participant will get the benefit of your presentation.
Yeah, yeah. Thank you, thank you. So there are two possibilities that they have understood everything or they have not understood anything. So let us see from the, in the next lecture we will see. So tomorrow we will be starting with cohort intelligence algorithm. It is one of the socio-inspired methodology. It is modeled from the behavior of the children playing in the park, how they are trying to learn from one another, and how they achieve the inherently common goal. So you will get come to know about a new algorithm field, that is socio-inspired algorithms. So see you all tomorrow. Thank you.
Apurva ma'am,
Yeah.
after this, there is a one question from the Pradnya Kulkarni too.
Okay.
CMO can be solved with the same way?
Okay, so I'll do one thing. Actually, I have some other commitment also right now. One meeting is there.
Right.
So this greedy algorithm and CMO tomorrow, first thing at the start of FDP, we will
Yeah,
discuss.
not an issue, ma'am.
Yeah, because we have taken complete 2 hours, so little behind the time.
Yeah,
So yeah, thank you.
thank
Yeah,
you very
so
much.
Pradna ma'am, tomorrow we'll definitely take your question and Suruchi ma'am's question.
Yeah, thank
Okay,
you
no
very much.
issues, ma'am. Thank you.
Thank you so much. Yeah, thanks for understanding. Okay, okay, Amit. So I'm signing off.
Yeah,
Thank you.
thank you, ma'am.
Thank you.
All the participant will get the attendance link in their group. Thank you, participant, for joining the session. Thank you very much. Shailesh sir, we are winding up.